All right, so the last chapter here is, of course, chapter 28, the structure of space and time. Um, another title for this chapter would be called cosmology, which is the study of the overall universe. We kind of started the study of cosmology when we started talking about galaxies. Um, all right, so these are the different things that we're going to discuss. We're going to discuss, Hubble's law, the Big Bang theory, which is the overall theory that describes the origin of the universe. This the idea of cosmic inflation, which is really just when the universe first began, it expanded very very rapidly for a very short amount of time. We'll talk a little bit more about general relativity, which is the modern theory of gravity. Of course, we have to talk about dark matter, which I talked about a little bit already with galaxies. Um, and then, of course, dark energy, which has to do with the expansion of the universe, which, of course, is that's what Hubble's law is all about. And then we'll talk about the final, what we think is going to be the fate of the universe as time goes on. All right, so let's get started. So in the 1920s, here's a picture of Edwin Hubble. This is he was an astronomer. He worked in California. There was actually two telescopes. There was the one. Well, the one that he's working on right here is called the Wilson Observatory, and it's north of Los Angeles. It's still there, but of course nowadays Los Angeles has so many lights at nighttime that it's almost useless. It's a really large telescope, and it was certainly very large at the time. Nowadays, when we build telescopes, we put them really far away from any population centers. There's really large telescopes, for example, in Hawaii, on Mauna Kea. There's some really large telescopes. I mean, they're all over the world, of course, but there's a really large telescopes in Chile to observe the southern sky. But anyhow, here's Hubble, and this. So these are some discoveries that he made. Actually, one of the first things or one of the most significant things that he did, at first, he did several really really important things. Is he used what's called a variable star, a star that varies its brightness in a very periodic manner, and so if you find a particular star, and you measure the distance to that star because of its period, you're able to measure the distance to the star. He actually found one of these same stars not only in the Milky Way galaxy, or similar stars that are in the Milky Way, and the same type of variable stars in the well, they didn't even know that Andromeda was another galaxy. In fact, back during before Hubble's time, it was kind of a hazy patch in the night sky. And of course, you had telescopes and you could take pictures of it, but no, people just assumed that the Milky Way was all there was. Like it was just our galaxy, and in fact, the idea that there were other galaxies was an ongoing debate at the time at Hubble's time. And of course, Hubble basically proved that the debate that Andromeda was one galaxy, and that there are, at his time, with the equipment that he had, millions of galaxies. And of course, nowadays we know that there are literally billions upon billions of galaxies, hundreds of billions of galaxies. All right, so Hubble's the first one to actually measure the distance to a galaxy. So he realized that there was something outside of the Milky Way, our galaxy, and Andromeda is actually the nearest large galaxy to us. It's actually about twice the size of the Milky Way. It's also a spiral galaxy, just like the Milky Way. I talked a little bit about that in chapter 27. Let's see. So he used the brightness of the inherent brightness of a star, by just looking at the period, and then he used this idea of the inverse square law, and the inverse square law, and so we encountered that in the last chapter as well. All right, so this idea of the inverse square law is really, really important, for all of astronomy. All right, so he figured out that distance. If the distance between your eyes and a lamp were in half, so the brightness, let's see, the light would appear to be 2 times brighter. So look, if you decreased it by 1/2, then it would become 4 times brighter, right? That's the idea of the inverse square law. All right, so it would be they messed that up. It would be 4 times brighter. I'm surprised they got that one wrong. The answer really should be C. It would appear 4 times brighter. I mean, you can actually do an experiment to prove that. If you ever take the astronomy, astronomy 102, we actually perform an experiment where you prove that. All right. Anyhow, that answer is definitely wrong. I'll try to fix it at some point. Anyhow, it doesn't really matter. It should be C. All right, so Hubble, Hubble noticed, of course, besides Andromeda, there were these other nebula, and he measured something called the redshift. All right, so this is also known as the Doppler effect. Okay, so you might have heard of the Doppler effect on television. Sometimes they talk about it when they talk about the weather. The Doppler effect, or it's also known as the Doppler shift. It actually goes by several names. It's basically what happens to a wave when something is moving. All right. So here's a nice little picture, right? So here's some guy standing on the side of the road, and there is a siren going off. And let's say the siren doesn't change its pitch, right? The pitch is exactly the same. So, but see, as the siren, as the fire truck or whatever it happens to be approaches this person who's standing still, they hear a higher pitch, and after the fire truck has passed by, the pitch gets lower, and so you can actually see what's going on here. So if the fire truck were just sitting at rest with respect to this person right here, there would be a certain wavelength that's coming off of this thing. That's the pitch. But if the truck is moving towards this stationary person, then what happens is the waves get scrunched together. They get closer together, right? And so that causes the frequency to go up. You hear a higher pitch, and then as the fire truck passes by you, the distance between the waves gets stretched instead of compressed, and so when they get stretched apart, what we do is we call that a redshift. So actually, conversely, when something is approaching something else, that's called a blue shift. All right. So if there's something that's approaching, it's blue. It doesn't, like, the sound. It's not blue or red. It's just a term that astronomers use because red light has a longer wavelength than blue light, right? And so we generally use that terminology of something being blue shifted because the waves are smaller than they originally were, or something is redshifted because the waves are further apart than they were. All right, so that's the idea of the Doppler effect. And if let's say, for example, this works not just with sound; it works with any form of wave, right? Any wave, and of course, light is a type of wave, and so light does this as well. Light gets blue shifted if the light is approaching the observer, and then it's red shifted if the light is moving away from the observer. All right, so that's the general idea, and that's so. For example, if a police officer pulls you over, if you're driving too fast, and they walk up to you and they say, "Do you know how fast you were going?" Which is for some reason the same. They always use that phrase, "Do you know how fast you were going?" They know how fast you were going because they use radar, right? The radar waves, which are just a form of light, bounce off the car, and that bounces back to them, and that tells them from the either the blue shift or the red shift. It doesn't, if it's approaching, it's a blue shift. It's moving away, it's a red shift. But there's electronics inside of the radar gun that'll, and usually a computer, of course, a little tiny microchip, and that'll tell the cop how fast you're going. Usually, of course, in miles per hour. Unless you're in Europe. Okay. So anyhow, that's the way radar works. And that works. By the way, that works for the weather as well, right? We have there's radar that goes out and can tell how fast like a cold front is moving, or how fast some rainstorms are moving. All right. How will the spectrum of a star moving towards us change? The wavelength of the light will be, it's not stretched. It's definitely not stretched. So if it's moving towards us, it's blue shifted, right? It's compressed. So B would be the correct answer. Oh, they got that one right. Okay, very nice. All right. So what Hubble discovered, you have to kind of remember back. In the last chapter, we were talking about like the local group of galaxies. There's us, there's Andromeda, and then there's several dozen, perhaps up to about 40 other galaxies that are around the Milky Way. That's called the local group of galaxies, and some of those we actually see blue shifts. So that there's some of those that are moving towards us, some of them are moving away from us. Like for example, Andromeda is moving towards us, and we can measure how fast it's moving towards us. And as I probably already talked about, Andromeda is actually on a collision course with the Milky Way. It's not going to happen anytime soon. It'll be 100 billion years from now. And keep in mind, the universe is only 13.8 billion years older. And so somewhere between 13.8 and 13.7 billion years old. So, 100 billion years from now is a long time. All right. So anyhow, we'll get to this thing called Hubble's law. So what Hubble discovered, and this was in the early 1920s, and he published his work in I think it was 1929, actually, is when he made this is one of the greatest discoveries of all time, right? Is he looked at so galaxies outside the local group. Every single galaxy that he looked at and made a measurement of, the galaxy was moving. It had a redshift, right? And so it not only was it redshifted, but it was redshifted in a very orderly way. That is, the further away the galaxy, the greater the redshift. And in fact, that's exactly what Hubble's law is. The further away a galaxy is, the greater its redshift. Now, it doesn't work for the local galaxies, the